Our last speaker for the session is Ilias Zadik from NYU.
Yeah.
Take it away.
Yeah, just let me fix a little bit my Zoom. Okay, hello everyone. Okay, hello everyone. Yeah, I will talk about the Planted Clique Model. So this will be a story that it is a little bit conceptually, if you want, similar with both the first and the third talk that we had in this section. So I hope you will kind of enjoy it. It will be a little bit more towards the algorithmic side of things. So hopefully you will find this enjoyable as well. Okay, so this talk is about the Planted Clique Model. So what is the Planted Clique Model? So it's a very simple random graph model that we denote by Gn half comma k. And it's very easy how to create it. I mean, it's a random graph model defined on the n vertex anti-radial graphs. So essentially, in the first stage, you just choose an Erdos-Renyi half. So you just flip a coin properly half for each edge. And then what you do is you choose k out of the n vertices, and you force them to the new subgraph to become a clique. So essentially, if you choose this k out of the n vertices, and if an edge doesn't appear between two out of these k vertices, you just force it and you add this edge. So for instance, you have on the bottom here, it's 7 vertices that are, you run your Erdos-Renyi, you create like this graph, and on the right, you choose 3 vertices, it happens to be these 3 red vertices, and you make this triangle. And then what is the goal? Like if you see it as an inference task is, of course, you erase the colors and you say, okay, I give you this graph. Can you find the hidden clique vertices? And the mathematical question of interest is for how small clique can you do this? So you can understand probably that, if I give you a very large k and, I hide a clique of very large size, you probably can spot it. But if it's very small, I mean, probably it's lost in the bulk. And okay, I mean, this is not I'm not the first one who's asking the problem. Also, it's an easy problem the way I stated, because what is happening. So if you put an axis here for the k, there is this interesting phenomenon that's arising. So if I just ask you to find the minimum k so that I can recover this clique, then there is if you want easy phase transition happening exactly at 2 log with base 2n. So if you have less, by using some standard random graph theory results, if I have less than 2 log with base 2n, then there is another clique of this size. And therefore, essentially, just from the randomness of the Erdos-Renyi graph, so you cannot recover. But if you have something bigger, essentially you can prove it's unique. Like the structure remains unique, and you can just exhaustively search among these k subsets, and you can find it. So far, so good. But there is a catch. And what is the catch is that essentially exhaustive search is somehow the best thing you seem to be able to do at this stage. Because if I ask you to deal with it only with polynomial time, so exhaustive search, takes n to the log n time, so it's super polynomial. So if you choose this k, n to the k. So if I ask you to do it polynomial time, the best result we seem to be having for many years now is when k is of order square root 10. So there's a huge gap where at this point we can just run a spectral method by this famous paper by Alon, Krivilevs, and Sudakov by 98. And essentially, if k is larger than this, we can do this polynomial time. But there is a regime where we basically, do not know what to do. Like we can try many algorithms, and like we can succeed all the way if k is that big. The clique is like square root n size, but we seem to be having this gap. And people have been thinking about it and said, okay, like let's try Metropolis chain, let's try some indefinite programs, or like many different polynomial time algorithms, and they can probably say that it fails. But this in the computer science world, you call it maybe there is hardness here. And in inference, this falls under a specific name of computational-statistical gap. And if you care about statistical problems, this appears a lot in regression, principal component analysis, and has been proven actually that Planted Clique, like this simple, essentially stochastic block model, at the first talk we were hearing, this toy model actually plays a core role among them. So essentially it has been proven that if you have an argument that there is no polynomial time algorithm working in this regime, you can transfer it by reduction to regression, principal component analysis. So it has been considered like an interesting kind of line of work. Okay, what I'm going to say in this talk is that with David Gamani from MIT, we are proposing a geometric perspective to try to understand what is happening at the square root 10 point. And I will show you some evidence, which is evidence like the anneal complexity we heard in the last talk, that k equals square root 10 is the phase transition points for the presence of what we call a certain overlap gap property in the space of dense subgraphs of this random graph model. And okay, what is this overlap property? I'm going to define it, but it's a property that originates in spin-glass theory. And it's known that it's like a bad landscape property, if you want, that when it appears, it suggests algorithmic hardness in some way. So essentially, this provides evidence that this square root n actually may play a fundamental role here, that it's not like a coincidence, at least in some point of view, that the algorithms break down at this point. Okay, and let me do a quick think of what is this overlap property. So it's essentially, overlap property, it's a lesson learned essentially by statistical physics and mean field spin-glass Hamiltonian, so there's a typo, I'm sorry. And essentially the lesson is as follows, that a lot of times in these models, we see a gap, between what algorithms can do and what essentially, if you want, exhaustive search algorithms can do. And I mean, polynomial-time algorithms, exhaustive search algorithms can do. And the lesson is as follows, that between easy and hard regimes, you can understand them as a phase transition in the geometrical point of view. And specifically that if you focus on near optimal solutions in the optimization problem you care to solve, then there is a really abrupt change in the geometry between the easy and the hard regime. A little bit less vague, but still vague, the way that people study this geometry is that they focus on the near optimal solution of the optimization problem, which of course usually random and everything. And they study how much does these near optimal solutions overlap. There's an appropriate inner product that usually you can define. How much do they overlap between each other? And then the prediction is that algorithms will work efficiently if and only if there are no gaps in these overlap sizes. So hence the name overlap gap property. And just some intuition, I mean, if there are gaps and there's disconnectivity, you expect essentially bottlenecks for the local algorithms. But if there are no gaps, essentially you expect that the local algorithm can navigate its way along. Okay, it has many names and overlap. Okay, so let's dive into the Planted Clique model of the interest of time of what could be this overlap gap property. So recall, sample from G and half comma K, you just have an Erdos-Renyi and then you plant a clique of size K, and you want to find. So there are reasons that I can discuss if you want at the end of the talk or in other town, like how to approach this, first of all, to define optimization problem here. And, in statistics, we say loss function to define appropriate loss function. I mean, what we do, and there is some reason to do this, is you fix a parameter K bar, which is something, it's a vertex size in between K and N, and you analyze the following loss landscape. You minimize overall the vertex, the K bar vertex subgraphs of the instance of the graph you have in front of you. And the loss is you penalize how much you deviate from being a clique. So you see the subgraph and you count the number of infused edges and you say, okay, how many edges are you losing from being a clique? Equivalently, this simplifies with what is known as a densest-subgraph problem, which seems fundamental potentially. Like, give me K bar and tell me how dense can a K bar subgraph can be in this Planted Clique model. And the overlap property is simple here. It says the following mathematical question. When does this property appear? That the nearly densest subgraphs of vertex size K bar, and dense I mean edge dense, are either the one that overlap with the clique a lot. So they are the ones who are dense because it happened that they contain a lot of Planted Clique vertices, or they're the one that use very little Planted Clique vertices and they use a lot of the randomness, if you want. And essentially, this is the question of the dichotomy of the overlap property, that essentially the bad landscape appears because you are dense either because you use a lot of the randomness or a lot of the Planted Clique, and essentially gaps in between. And there is, of course, I'm jumping a little bit fast, but like that's kind of the mathematical question that arises. Because there's the course definition. Okay, so how do you study this problem? I mean, okay, we are trying to understand, of course, whether this phase transition with respect to these landscapes appears as a square root n. That's the question. And, how do you study this? I mean, the most natural way to study this is to fix, essentially do some anneal complexity, but I will explain how to do this, is you study the following random function, which fix a level of overlap with the Planted Clique, let's call it Z, and tell me how, what is the optimization you can do in this restricted sense? Like if you have this overlap, how small can you make the loss? And it's natural to think about that this is actually the key quantity here because, okay, first of all, to be informative, this loss should be minimized when you contain the clique, when you have full overlap with the clique. So essentially the arg mean should happen at Z equal K. So there is some technicalities there. But essentially what drives the picture is the monotonicity of this curve. So if this curve just dives, in a monotonic way to Z equal K, then actually you don't have overlap property. And the opposite, if it has a bump first and then it goes down, actually you can prove by some simple calculus argument that essentially, this is really mean that you have like a property because you are, minimize the corners if you want. And essentially it becomes a question of monotonicity of this random function. And then, okay, you can say how I'm going to study this. So, I mean, you do first to get some intuition, you do some trick like the anneal complexity. And you do like what we call a first moment boundary random graph theory, which essentially, if you want a fine grained union bound, which is, what do you do is you say, okay, how small can I make this? You can take a lower bound on this curve by just some, appropriate large deviation theory, like lower bound, and you get like this falling deterministic function, which is what you get by just large deviation theory. And you can ask, okay, it's a complicated function, but it's a deterministic function. How does this behave? And if you do this, we arrive at the following conjecture that I think it's an interesting phase transition. It suggests an interesting phase transition, assuming that the behavior of the lower bound is the same as the behavior, of course, of the upper bound, which says the following thing. If this Planted Clique size is less than square root 10, which is what we expect to be the critical thing, you can tune this k bar. If k bar is small enough, then the function is non-monotonic, and therefore you have overlap property. But if you go a little bit above this k bar, then actually the function becomes increasing. And in particular, the minimum is not when you contain the clique, and that you are uninformative, as we say. So there are only bad scenario if you want in the one case. But in the other case, if k is bigger than square root 10, then if k bar is small, you are non-monotonic again, and you have overlap property. But if k bar is bigger than this and smaller than a threshold, there's a sweet spot above the square root 10 that actually the function is decreasing, which is the good case because you have no overlap property and you're uniform. Of course, that can be confusing. So I have like this following figure here. This is, it has k here and k bar here. And so you see what's happening. Like if k is less than square root 10, on the left, there are either two cases. Either you're hard below this orange curve, or above you're uninformative but easy. And on the other hand, OGP, you're either hard or you have a regime where uniformative and easy. And therefore, we suggest essentially this anneal complexity or first moment, if you want, picture that's happening in the landscape. And then, of course, you can say, okay, like similar to the previous talk by Benjamin, you can ask, okay, how much have you proven out of this? That this is actually the transition in the dense subgraphs. It's easy to prove kind of the easy parts here, so I'm not going to mention. I'm going to mention about the OGP part. And here we have a result. We have a result that for part of the landscape, indeed, there is overlap property, this connectivity property, that at least if you are in some small power of n, indeed, the picture suggested we prove tightness to the lower bound by second moment method. And we prove that indeed this overlap property holds in the landscape. So, if you want a small part in the beginning of OGP. And I want to dive a little bit into this random graph for the last minute, if I have. So like of how do we do this? So this relates to potentially fundamental question in random graph theory. So it relates to the question of what's the densest subgraph problem. So forget everything about the clique. Just I give you a random graph, an Erdos-Renyi graph, and I ask you, and I give you a k, which is a size of the vertex size, and I ask you how large can you make the density of the induced subgraph of vertex k. It relates, of course, when you have zero overlap with this gamma k, that's what we care. And surprisingly to us, actually, this is not like a solved problem in random graph theory. So it's as opposed to, for example, what's the maximum clique size, or that we know a lot of results, or the chromatic number. This is interestingly kind of limited. And the best result goes to this work by Paul Barristan and Bella and others from 2018, that they prove that if k scales logarithmic with n, actually there is 2-point concentration in this optimization problem, and they exactly specify what is the quantity. And essentially, they prove tightness to the first moment. It's a second moment argument. And then what we did was we took the technique and push it, and we push it to the polynomial size of k. And by introducing an error term, so we couldn't prove 2-point concentration, we introduced an error term in what we do, essentially again by proving tightness, with the second moment method. And just to give you an idea of what is this error term, the first two terms become, they don't change. Essentially, it's a third order connection. And then, of course, how do we do that? And this allows, of course, that's why we got the little power of n, if you want, improvement. And, just a quick comment, this vanilla second moment fails, and we need to prove appropriate conditioning, because, if you do the second moment method, of course, there are all these various ways that dense subgraphs can overlap, and you need to control them. So, it takes, of course, a lot of care, and, like on how to actually do this, I invite you, we can discuss, like in the paper, to see this, and, that's it. Thank you very much for your attention.
Okay, so I'm gonna stop the recording.